And so our next presentation is also a virtual presentation by Alex Sokołowska. So Alex, I will let you go ahead as soon as you can and share your screen. And this talk will be on open sourcing a reconstructed catalog of new impacts on the moon.
Thank you. Hopefully you can see this.
Yep, absolutely.
Yeah.
All right, we're going to go ahead and mute the room. You can go ahead and get started whenever.
All right, thank you. So good morning, afternoon, and evening. My name is Alex Sokołowska. I'm a research fellow at Imperial College, and most of the people on the team who contributed to this are at Brown. And I wanted to use this planetary creator consortium platform to announce that there is this catalog of new impacts available now to the planetary community. Yeah, okay, whatever. I wanted to switch on my camera, but now it's actually more complicated. I'll just go on without it. Uh, so I will talk about the motivation behind this in the end reproducibility study, and then describe how we reconstructed the data set, talk about what's been published and what we're actually doing with this data. So I'll just dive right in. And the new impacts as a term, as I will be using it, it refers to impacts on planetary bodies that have been found in the period of spacecraft observation. So in the case of the moon, one of the first new impacts has been found by comparing Apollo data from 1970s with LROC-NAC data in 2009 that permitted date constraining to 38 years roughly of that prominent impact that you see zoomed in on the right. Not all of the impacts, and I would say the majority of the impacts look very different in the sense that they're under-resolved and you might not be able to maybe see that many details about the morphology of the crater and so on. Nevertheless, I am hopeful that I can make the case here that studying new impact sites and particularly having access to a database that has the locations of these new impact sites is going to accelerate lunar studies on a variety of fronts. So starting with the nature of the impact process, the new impacts on Mars, that is true, but also to some extent also on the moon, they are surrounded by very distant features in the dust and regolith that sometimes extend by 50, 100 times the crater diameter. So on Mars, we can see, the effects of the bow shock coming from the meteoroid. There's blast waves coming from the impact point. There's blast waves from the ejecta curtain cutting through the atmosphere. We also have vapor plumes that are the vaporized target and impact winds. There's a lot going on that's extremely understudied. And so these new impact sites have those features on the planetary surface preserved because they have not been weathered or eroded yet. So it's very valuable to have that data. In terms of the structure of planetary subsurfaces, by using the crater morphology, inspecting ejecta, whether there's rocky or non-rocky ejecta in it. And very recently, I also talked about this 2 years ago as a proof of concept at this meeting, which is now the topic of my fellowship. It's basically the idea that we can use the ejecta radius or the spatial distribution of ejecta as a subsurface probe. Because what happens to the impact energy during the impact is that some of that energy is being absorbed, some of it is being transmitted through different layers, some of it is reflected, and that turns out to be a unique fingerprint in many cases. This is the paper that has been published this year. If you're interested in that, I would like to refer you to this. I used ISIL shock physics code and 7 different subsurface structures to show that small impacts in strength dominated regime can really have that feature as a fingerprint. And then more obviously impact cratering rates. We need to know at what rates and what sort of sizes of impactors are threatening Earth. This is particularly important now during the rise of the planetary defense when all politicians do want to know what is the size of an asteroid that is going to hit potentially Earth in a very reasonable time. And then there's an aspect of the luminous efficiency. So we don't really understand much about radiation coming from impacts. Our understanding stems from nuclear and chemical explosions. And only recently, in the last decade, we began to observe the so-called lunar impact flashes, so the actual few second long radiation signal coming from new impacts. Now, for the first time in human history, there will be a lunar orbiter. It's called Lunar Meteoroid Impacts Observer, in short, LUMIO, a European CubeSat that will be observing impacts on the far side, and it's projected to be able to capture about 10,000 impacts per year. And so we will be able to now finally understand luminous efficiency, that is a fraction of impact energy that is being radiated away. And finally, one big application is if we actually understand and know where the impact location is, and at the same time there was a seismic instrument that recorded the seismic shaking, this basically limits or deletes one of the variables in interior structure modeling, which is a distance from the event. So hopefully, that overview kind of summarizes that there is value in having a catalog of new impact sites and that it can permeate into a variety of subdisciplines in this impact cratering field. In terms of Mars, I think that Mars is a very good example of how the community is categorizing and archiving and openly sharing this information with the community. For example, in 2022, there was a research paper by CurieWac staff and some people also who are collaborators of mine who released a deep learning data set. And as you can see in this table, there were latitudes, longitudes, and some other features, effective diameters of 69 deep learning found craters. Later that year, my mentor and previous boss from Brown, Ingrid Dauber, she released a catalog of over 1,200 new impact craters on Mars, which contained observation IDs and identification of a lot of transient features related to different impact process-related processes, like halos, rays, and so on. Very recently, I was involved in that work. We went back to the data from CurieWac staff deep learning model and we pushed it down to a very low confidence threshold. We focused on the area near InSight and found even more new impacts and tried to match them with locations. So in any case, like in terms of Mars, there's a lot of data out there in tabular form on locations and characteristics. I see comments coming, but I can't read them. So hopefully this doesn't mean that people don't hear me. In terms of lunar impacts, the information
I
is a
can hear
little.
you, you're good. People were asking for the link to the database, which I then put in the chat.
Awesome, thank you. So in terms of lunar data, it's a lot more fragmented. So we might have some research papers that will, in a very nice way, report on latitudes and longitudes and crater diameters of a few. And every now and then, when there's a big one, then there's a paper about the big one. You can probably find that. There was a very important paper in 2016 coming out that actually did a very comprehensive search and reported on the sightings of 222 new impacts on the moon. Unfortunately, the way that the information about the location has been presented is only in the form of the map that you can see here, and every individual point on the map is the only way how you can figure out where it is. So of course you can try to get the data. I tried, I didn't manage to, but in any case, there's a way to do this and give it to the community as a table like we do in the case of Mars. So I convinced my boss at the time, Ingrid, who's a co-I on the Lunascope, NASA Survey new funded research institute. And she also had a NASA SSW grant related to impact cratering rates to spend a little bit of money on hiring undergraduate students. So we got two students, Jonah and Sierra, who did a lot of manual searching for these individual craters. And then later also we got Tiffany Gao, who could put tighter constraints on formation time of these craters. And also postdoc hired well on the Lunascope funding. Dr. Reisich was involved in this study. So what did we do? We basically took brute force approach. We took the maps from Speyer et al. 2016 and tried to extract after georeferencing the approximate locations of these craters. As you know, this is map projected. There's distortions, so sometimes we're pretty much off by kilometers. So we needed to narrow down the parameter space. We did this by using extra info, like there should be neck image pairs, they should have similar lighting. Later, we also georeferenced the extended figure that showed the distribution of neck pairs that were considered in this work. That helped us narrow it down even more. Then we ended up having LROC neck candidates that we later read in QuickMap and verified in QuickMap that there was a crater. And when we found the crater, then we mapped it and measured its exact coordinates, crater diameters, and tried to put the best date constraints on the formation of that crater. So overall, the very limited funding that we had for this reproducibility study permitted us to search about 95 out of 222 areas. 69 new craters were found. That means there was about 73% success rate with this method. And we also found 8 new impact splotches. Now, it could be that some of the splotches were identified by Speyer et al. As craters. But it could also be that they were just collocated, because I think the paper reports over 14,000 splotches that they've also somewhat found during their search. So in any case, that's what ended up in our data set. So I'm showing you here the map of all the 69 reconstructed new craters. As you can see, we didn't focus in one specific area, but we tried to cover as interesting geological areas as only possible. The diameters go from 2 to 16 plus meters of these craters. They are found in Mare, in highlands at different latitudes. This is the collage of what all of them look like. So we have 69 new craters and 8 splotches. So this is also shown in PDF on Zenodo. The reason why I did this is because I thought it would be very useful for people to just have a nice reference to quickly go glance at this and think like, oh, I'm interested in crater 18. Let me go to the CSV, see what the latitude is, and then you can pull it out and study it. This is what Zenodo looks like, and there is also a GitHub page encircled here. I will cover this in a second, but what I want to highlight is
You
Sorry?
have 2 minutes.
Yes, I have, so there were about 40 something downloads, even though this thing has been advertised yesterday for the first time and today. So I think people are interested in this data, which makes me very happy. The dataset online has 80 something locations. That's the 69 craters reconstructed, plus some from literature, plus impact splotches. The data contains the PDF with thumbnails, as I mentioned. But also, I want to highlight what I put there is the list of approximate locations where we didn't find craters, but they should be somewhere in a wider radius. So if someone has resources and the need to go into this data and invest in searching better than we did, then you can. There's a CSV with crater locations, lat long, latest before and after IDs, and formation times, same for splotches. So if you end up using this data set, it would be awesome if you could cite the PCC abstract. The PCC abstract contains the Zenodo link, and also obviously the original papers where the data comes from. And then if you do find new craters that are not on the list, I want to just appeal to the community to expand the list and do this in the following manner. You can use GitHub page that kind of mirrors this. If you expand the CSV using the same schema, this is basically a table, and then make a pull request, I can review it, and I can then update also the dataset on Zenodo, cite your paper, and add your contribution. That's kind of a little bit of a service that I would like to entail into part of my work to maintain this and ensure that people have access. What we are doing with the data is at the moment is studying the environmental effects of impacts. That's ejecta, and this kind of blast zone mapping of these craters is ongoing. That's work with Brown. We're trying to match impact flashes with this data that's in preparation for the Lumio mission with people in Leicester. We're training a lunar impact crater machine learning detector. That's the collaboration with people in Bern and Paris, and I'm getting a master's student who will start doing ISO simulations of new impacts. Everything else, in terms of topics, is up for grabs. So for those who like QR codes, you can scan it and get to the Zenodo. I would just like to say that everyone is invited to contribute, and if you have any questions, you can email me. I'm done.
All right, thank you very much.